Hi there. Welcome back on this fall afternoon. Weather analysis with Mr. CB. So, we're going to be talking about some cool things today. We'll start out with reviewing jet streaks. So, if you remember, jet streaks are areas within the jet stream. They are localized areas that happen to have stronger winds. And the reason why that is that the areas where these jet streaks are have stronger thermal gradients. So as just like when we're looking at our surface maps, we know that for the surface maps, if we have closer multiple pressure lines that are close, that means pressure is changing quickly. Same thing for when we're at the high levels here, because remember, the levels that we're looking at for this is going to be something like a 300 millibar map, which would mean everywhere on that map is 300 millibars. But there are differing heights that are shown by the ISO height lines. And here, there's going to be a stronger gradient, so stronger change. Um, and so we can use where these jet streaks are to help determine upper level convergence and divergence. And so we'll see how that is. Okay, so what will a parcel do as it moves through a jet stream? So you can see this jet stream here. These lines here indicate, or these lines indicate this is the flow of the wind. So the wind is going from west to east generally. Um, we have westerlies as we know, but the general movement of the wind in our country, United States, assuming if that's what you are in, um, winds are going to be moving from west to east. So we would at least know that. We would also know that something like this, once again, everywhere on this map is going to be a constant pressure, but differing heights. There's going to be lower heights up here, higher heights below. If you remember in the last video, to the left of the flow is low. To the left of the flow is the low, if you want to remember that. And since it's going this way, the left of the flow is right here in the north. So in a situation where the winds are going directly horizontal, to the north will be where we have lower heights, but higher heights below. Ooh, sorry about that. Something just fell down. Um, so this area that looks like an oval is what we would have as our jet streak. So what's the parcel going to do when it gets into this thing? Is it going to just do nothing? No. That's why, we have this video. So here's what it's going to do. Now I know that's a lot there on this slide, but I'm going to walk through it. So you don't have to worry about reading all of that crap if you don't want to. I'll just say it. So, as we know, ugh, sorry, that just hit my computer. Um, as we know, this is probably not the best place to make this video, honestly. I'm beside a road too, so um, anyways, I just wanted to be outside today. So we have geostrophic balance generally in these upper levels. Remember we talked about that before. Remember that video I made with the train tracks. Pretty glad I have a hat on right now, honestly. So uh sorry. But something will change though once we get into this jet streak. No longer will there be geostrophic balance. And if we have geostrophic balance, remember that means the two forces that we have are balanced. And what are those two forces? Pressure gradient force, Coriolis force. Review what those are if you don't remember. I won't really say, but we at least know that pressure gradient force is always going to point up um in a jet in this flow that is horizontal. Why will it point up? Because it points from high to low. And remember I said to the left of the flow is the low. The flow, see the green arrow, is to the right. So the left of the flow is the low. The pressure gradient force points to that low, points from high to low. Coriolis force is always just going to do the opposite of what the pressure gradient force does. So that's why it's pointing down. The flow is moving to the right because, like I said, west to east flow is what we have. But what's going to happen when we get into this thing? So first of all, there's going to start to be stronger winds in here. Remember? I said it's an area of localized strong winds. Well, since there's stronger winds, that's going to cause the pressure gradient force to increase because we have a tighter gradient here, tighter gradient between our heights. So that means quicker movement from basically the range of heights that we're going through is larger. And that would cause the pressure gradient force to be stronger because it's like move through that faster because there's more heights to go through. If that makes sense. The pressure gradient force is going to increase, and that causes it to be unbalanced, which means ageostrophic flow. And in that case, now the wind is going to move up. See? Now it went slightly this way. Within our flow, it went up or north. But eventually, towards the middle of this thing, they're going to get balanced out again because Coriolis force will eventually increase to balance that out. Because remember, that's how that goes. And it's just delayed, so it doesn't do it right away. It waits a little bit. So now, once again, there's geostrophic flow where both of these orange arrows are. But then, once we're exiting the jet streak, the pressure gradient force goes back to normal. See, now it's the black arrow again. But the Coriolis force does not. It takes a little bit. Once we're over here, then it'd be both black again. But if you see the different colors, orange or black, or all orange, if it's all orange or all black, we're in geostrophic flow. But if it's different colors that I'm having here, then that's saying we're ageostrophic. Here, now, since the Coriolis is stronger, it's going to move right back down, and we're kind of back to normal once we get out of this thing. So that's exactly how this works. So you can see this right here. We have the jet streak. There's stronger winds. Stronger winds means a steeper, tighter thermal gradient that will cause pressure gradient force to increase, and there's an imbalance, and the parcel will move more north till they balance out. Then as it exits, then it's going to move south because Coriolis is stronger, but then eventually go back to normal and they balance out again. Within the jet streak, we also have vorticity. Vorticity in its simple form, if you wanted to say, it's just spin. Where there is vorticity, we will have air rising, but it also will depend on, we'll look at this later, depending on where this is going and what direction it's going. But really, right now, just consider it as a spin. To look at vorticity, we typically instead look at a 500 millibar level. So that means a mid-level of the atmosphere. We'll talk more about that in a future video of these mid-levels. We can still have pressure gradient, or sorry, we can still have vorticity in the upper levels though, which is really what we can know because if there's a jet streak, we can have vorticity. There's two types of vorticity, planetary and relative. Planetary, we're not going to talk about that much right now. That's due to Earth's rotation. Relative, though, is what we really will discuss. And there's multiple different designations within that. So relative vorticity is based on wind flow and wind speed. All of what I'm about to say is only true for the northern hemisphere because that's what we're really studying, in weather, but it would be reversed in the southern hemisphere, just to let you know. But we can have two types of this relative vorticity. We can have cyclonic or anticyclonic. Now, there's multiple names for the same thing as there sometimes is, but cyclonic is positive, anticyclonic is negative. If we have cyclonic, all right, sorry about that. I had to stop the video real quick. But I was saying that for relative vorticity, we could have cyclonic vorticity, which is we're going to have air rising. It's going to be counterclockwise. We call that positive. Anticyclonic is going to be sinking air clockwise, and we call that negative. Within that, this is such a bad place to make a video. So within the relative vorticity, we could have curvature or shear, and we're just going to look at that before I talk about that. So this is going to be curvature. So we're going around a curve. All these different things go together, so you'll want to just remember these as pairs. If we're going through a trough, think about that. The wind's flowing this way. If this is like a pinwheel or something, it's going to go spin it that way. That's going to be counterclockwise, right? And if we know that's counterclockwise, that's considered anticyclonic. That's considered positive also, and it's considered or it's where we would have rising air. Now, opposite for this ridge, we can see that the wind blowing around that's a clockwise motion. That's considered cyclonic. We'll have sinking air, and it's considered negative. So that's curvature vorticity. Shear vorticity has to do with um, wind speed above or below. So you can see that in if we have assuming that this white box like is just that basically stream of wind flow, in the center of that is going to be the strongest winds, weaker winds as you get to the top or bottom of that flow. And so if you just imagine if you had pinwheels here or there, what is this going to do? If you have a wind that's blowing this direction, it's going to spin it up like that, which is counterclockwise. But the one down here is going to go spin it down. Imagine that wind blowing, it pushes against that. Imagine like a gear grinding, like it would make it go clockwise. So basically, above fast winds is going to be counterclockwise, and below it is going to be clockwise. So that's actually written reversed. So sorry about that. Because you can see above the fast winds, it's going counterclockwise, and below it's going clockwise. So sorry about that. I don't know how that happened on here. So that's reversed. So just to let you know that now it's right. So that's what we would call shear vorticity. Now you look at this together. So in within the jet streak. So this is a lot to look at here, but as we know, okay, we're like I said, we're gonna have that L above, that H below. What we're looking at here is going to be what we would call jet streak dynamics. We're looking at vorticity and movement within the jet streak. Um, and we can see it counterclockwise above, clockwise below. That's this right here is because of our shear vorticity, because this is the fastest wind. That longest arrow indicates the longest magnitude or largest magnitude. So in the center we have of this jet streak, we have the fastest winds. So above is going to be counterclockwise, below is clockwise. That's from our shear vorticity that we just talked about. Um, and ahead of a counterclockwise flow, we would have what is called PVA, and that is going to be positive vorticity advection. And that positive vorticity advection is going to be having divergence associated with it, and rising air, because we know, remember from the last video, well, not last one, but recent one, um, that divergence results in rising air. Why is that? Because remember, it's like the fast car speeds up and leaves the slow car behind. There's a gap created. Air rises to fill that gap. That's why air rises at divergence. So we have those two associated with each other right here, divergence and positive vorticity advection. So we know that ahead of a counterclockwise flow with this shear vorticity, we will have rising air. And in a minute, we'll talk about how that's nice to know. Behind that, on the contrary, we'll have the reverse. NVA, negative vorticity advection, and convergence behind it. And then we know from what I talked about that the wind is going to generally go this way, north, because of the pressure gradient force increasing. But we can have a mirror below it. So the above part is really what will matter more for us. Below, it's just the same thing but flipped around. So clockwise, now the convergence in NVA is over here, PVA divergence over here. The PVA is always going to be you can see the arrows like dun, dun. It's going to be ahead of that flow. So how oh sorry. So that's circled because we're going to say yes, ahead of vorticity, we would have to watch out for storms and precipitation because where air is rising, we might know that. So that's what ties it all together in this video. So all this stuff might seem random, like what's the point of that? What's the point of that? Well, all this to say, if we look at the upper level map and we see vorticity, um, and we can know that ahead of it, we may have rising air. So that's all this to say that. So here's a map of vorticity. Vorticity on its own, as I've said, is shown at 500 millibar around that height. Usually, that's what that mid level of the atmosphere is useful for. And we can see that by these values down here, that purple is going to be higher vorticity. So let's just look right there, for example. Well, we can see these ahead of that. We know that the wind's going to be flowing this way. Ahead of that, and right here, we might say we would expect some storms or precipitation. You can see this is from today. Well, let's look at what the severe weather outlook is for today. Well, it just so happens that we don't really have any high risk at all, but the risk that we do have is marginal, but it is ahead of where this vorticity is. That does make sense. So this is going to be something that's useful for us to possibly know where we might have storms or precipitation. So that's going to be it for this video. Thanks for watching and enjoy your fall day.